Hello and welcome to Skill Lab, a place where knowledge is shared. Today, we continue our series on oxygen, by better understanding the primary physics behind gas dissolution in water. First, let's review some concepts around gas saturation that we already discussed in the last episode. When a gas cannot be dissolved anymore in a liquid, we can say that the liquid is saturated. We have reached 100% of saturation. Saturation is a function of temperature, salinity, atmospheric pressure and altitude. So, you always need to keep these three parameters in mind when you are thinking of gas dissolution in water. Let's start by understanding the fundamentals of gas dissolution in water. First of all, Dalton's law states that, in a mixture of gases, the total pressure exerted is equal to the sum of the partial pressures of the individual gases. Air is a mixture mainly of nitrogen, oxygen, water vapor and a little CO2. So the atmospheric pressure equals to the sum of the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of water vapor plus the partial pressure of carbon dioxide. Then, we need to know Henry's law, that states that the maximum amount of gas dissolved in a liquid, saturation, is proportional to the partial pressure of this gas above the liquid. A gas always moves from the place where there is the most to the place where there is the least. Once we learn that, we understand that oxygen, 21% in dry air, can dissolve in water at a fixed ratio, without any artificial intervention. Let's understand better how we can intervene to change that. When a gas molecule hits the surface of a liquid, it may be deflected back into the gas or dissolved into the solution. Three main factors influence the gas transfer: the contact time, the exchange surface, and the pressure. So, when we think or evaluate a system, we have to consider that the more parameters we can control, and the better we can control them, the better the outcome we get. Contact time. The more time a bubble of gas stays in the water, the more it increases the dissolution of this gas. Exchange surface is represented by the ratio between the volume of a single bubble of gas against the surface of the bubble itself. The highest the surface, and the smallest the volume, the more gas will be in contact with water, and thus will be available to transfer. Pressure. As you increase the pressure of a gas, the collision frequency increases, and thus the solubility goes up. As you decrease the pressure, the solubility goes down. Shortly, the system that can keep the bubbles in water the longer is best. Tiny bubbles need to be preferred to large ones. A higher pressure needs to be chosen to a lower one. At this point, you understand the factors that influence the dissolution of gases, and so the dissolution of oxygen in the water. When designing or choosing your aeration and/or oxygenation system, you need to control and combine as many of them as possible to obtain the best results. Aquamiks tip of this episode is yield versus efficiency. To choose your oxygenation system, you have to keep in mind loads of parameters. But you can never forget that you have to find the right balance for your situation, between the yield of the system you are implementing and its efficiency. Economic and material resources are limited and need an accurate balance. Thank you for being part of the aquamiks community. Remember to subscribe, like and share this video to keep learning together.